Okay, in this problem, we previously looked at how to get the constraint over here and the objective function, which is the surface area that we're trying to minimize. And so we got the objective function surface area in terms of one variable x. So now we need to finish the problem. So we're going to differentiate a surface area to get this, set it equal to 0 to find the critical values, and solve. Here's all the solving. I got x is 10 in this problem. Okay, so we need to check that that is in fact a minimum on the surface area at x is 10 and not a max. So the volume is 500, which means x can't really quite get to 0. I mean, it could get infinitely close to 0, but the interval for x would be from 0 and really out to infinity, because you could just make the box infinitely flat and still have a volume of 500. So to check, I used the second derivative test. So derivative of x squared, oh no, right here, the derivative of 2x is this 2, and the derivative of this term becomes positive 4,000x cubed, which if you write it as a fraction looks like this. And for any positive value of x that you plug in, this is going to be a positive number, which tells us that A, surface area, is concave up. So by the second derivative test, there is a min at 10. So then all you need to do is go find h. So I use this right here. We had already solved for the constraint, h is 500 over x squared, and plugged in 10 into that denominator to get 5 for the height h. And then the last step would be to actually find the minimum surface area, which you could come back to the first equation we wrote and plug in x and h, or you could plug in x on this surface area equation here. Either way.